Convex gains, and Maxwell will give the talk. Cool.
Hey everybody, I'm Max. I'm here to talk to you about some recent work on linear correlated equilibrium in games. This is joint work with Kostis, Gabriele, Haris, and John. Cool. Okay, so I want to talk about online learning, okay? In the setting of online learning, we have some convex set in Euclidean space. And we have a learner who is going to repeatedly select an action from this convex set, okay? So at every single time step, the learner selects an action and then observes some loss vector, okay? In this time step, they incur the loss that is the inner product of their action and the loss. Cool. They repeat. At every single time step, they try to adapt to the loss they've seen, continue to incur some loss, try to learn over time. What's important about online learning is that these losses are selected adversarially. They're not coming from some distribution. Okay, so, we have this set P, which is our action set. For every time step T over capital T times, we're going to, select this action PT, observe a loss from, let's say, the hypercube, and incur this loss that is the inner product. Okay, so over capital T rounds of learning, we can compute the total loss of this learner. But in the setting of online learning, we don't evaluate based on total loss, we evaluate based on regret, which there's many different ways to define regret, but it's always going to be some comparison of the total loss of this learner to some sort of benchmark. The classic is external regret, where what we do is we take this fixed sequence of losses, and we compare the loss of the action selected by the learner to the best fixed action over all the possible actions in P. Right? So that's this quantity, the total loss, versus the loss of some fixed action against this loss sequence. What we're interested in this paper is studying the stronger notion of regret, which is linear swap regret. In linear swap regret, we compare the actions of the learner to any linear transformation of the actions of the learner, okay? So what we're going to consider is the set capital Phi of all linear transformations mapping the set P to itself. And then we're going to compare the total loss of the learner's actions to the total loss of a transformed sequence of actions, the best possible transformation, or worst possible. This captures external regret, right? Like these constant maps are linear. But now this is a much larger family of benchmarks that we're going to try to meet simultaneously. If we can meet this stronger notion of regret or minimize it over time, we have additional guarantees, such as, as discussed in the previous talks, like conversion to a stronger notion of equilibrium, and there's also results showing that these learners are robust in certain strategic settings. Okay, so let me just talk about the punchline of this talk, all right? We're going to minimize linear swap regret over a completely arbitrary set of actions, okay? We're not going to assume that the set of actions is nice at all, has any concise description. We're just going to assume that we can efficiently query this action set. So we can efficiently check if a action is in P or not in P, okay? That's all we have access to. And so the thing is, we want to compute or minimize our linear swap regret, which is, in terms of this set of linear transformations. But in this totally general setting, we cannot efficiently check if a transformation is even mapping P to P, okay? So here's an example of this, right? Let's just say that I give you this action set P, which is like a high dimensional sphere. And maybe I cut a cap off of it somewhere, but maybe I didn't. I don't tell you, okay? Now, you can query points in the sphere and try to search for the cap, but if you were really trying to determine whether or not there's a cap missing, you'd have to make exponentially many queries in the dimension, okay? So you can't effectively check if there's a cap missing. So then, if you consider this linear transformation, that's like rotation around a pole, you don't know if this linear transformation maps P to itself, right? Like, if there's no cap, then yeah, this is a endomorphism on this set. But if there is a cap missing, then, part of the sphere will be rotated out of the cap, and this is not a linear endomorphism. So in this very general setting, that is the focus of this paper, you can't even tell if this phi is one of the transformations you're going to have to compete against, okay? You can't even compute your linear swap regret, given a sequence of history. And yet, you can minimize your linear swap regret. without knowing what it is. So that's kind of cool, and that's what we're gonna do in this paper. All right, so let's talk about regret minimization. We'll start with the classic external regret, okay? So, what we want is some algorithm that's taking in losses as inputs and producing actions as outputs. The classic algorithm is follow the regularized leader, okay? You'll consider some sort of cumulative history of the losses that you've seen, and you're gonna choose the best fixed action, or the best action historically, but with some additional regularization, okay? You add some strong convexity to add some smoothness to your algorithmic decisions. Okay, so, this algorithm, appropriately regularized, has this guarantee of having a sublinear square root of t external regret, okay? Meaning that as time goes to infinity, the average regret converges to 0, which is cool. Okay, what does it take to run this algorithm, right? So in order to run this algorithm, at every single time step, we have to solve this minimization problem, minimizing some convex function over this set p. The classic, ellipsoid style algorithm stuff mean that, we can do this optimization as long as we can do separation over p, meaning that we can either confirm a point is in P or separate an exterior point with a hyperplane. That itself can even just be boiled down to membership. As long as we can efficiently check if a point is in P, we can do separation, we can do optimization, we can run FTRL, we can minimize external regret. All we needed was membership. So that's good in this setting we're considering. Okay, what about this linear swap regret? So let's discuss a classic algorithm for linear swap regret minimization that was due to Gordon, Greenwald, and Marks. Okay, so classic algorithm, again, is going to be mapping losses to actions. And the key idea of their algorithm is to essentially reduce this swap regret minimization over P to an external regret minimization problem over the set of transformations, capital Phi. Okay? So this is an idea you haven't seen before. It's kind of cool, right? First thing, you can, obviously re-express this vector matrix vector product as the matrix product with the tensor of the action and the loss. And so what our algorithm is going to do is, as a subroutine, we're going to have a FTRL instance over the set of transformations, the set of matrices capital Phi. As input to this subroutine, we're going to pass the previous loss and the previous action we answered. This algorithm is going to suggest some sort of transformation, and then the actual thing that we output will be a fixed point of this transformation, okay? So again, this phi is going to be a linear function mapping p to p, right? And because it's an endomorphic continuous map by, for example, Brouwer's fixed point theorem, there is some p in my set capital P that is fixed under this linear transformation. And so this is guaranteed to exist, and applying this guarantees what? Well, we have the external regret guarantee of our FTRL instance, right? So that's going to say we're going to compete well against the best fixed phi star. But then if you look at this first term is just equal to pt by the fact that we selected this p to be the fixed point of this phi. You can replace this term with this term, and you've arrived at phi regret minimization. Cool. Okay, what did it take to run this algorithm? Okay, well, there was this component where we had to compute the fixed point of a linear function. That's going to be doable. But now that we want to run FTRL over capital Phi, we need membership over capital Phi, which we don't have, right? So okay, linear fixed points we can do. If this is our set P, in D dimensions, what we can do is just minimize this convex function over P, right? So that's going to have a minimum value 0 at some fixed point. On the other hand, now we have this set capital Phi that's in, again, D squared dimension, right? This is a linear transformation matrix. And we cannot efficiently check if a point is in Phi or not, as was shown by the capped sphere example. Okay, so what do? Well, okay, if you look at this part of the proof, where we're using the fact that, we have an endomorphism, like capital Phi, we're realizing that, all we really needed was that our Phi that we selected had some sort of fixed point, right? That was just kind of the key of this step of the proof. So why are we optimizing, why are we trying to minimize regret relative to the set of endomorphisms? Why not minimize regret relative to the set of all transformations that have a fixed point in P, right? That seemed to be what was the necessary step of the proof, right? As long as we have a fixed point, we can, select a P that is fixed relative to that. So, the set of fixed points is, right, a superset of the set of endomorphisms. Endomorphisms have fixed points. So we could, minimizing regret relative to all of the transformations that have fixed points would certainly be sufficient to minimize regret relative to the set of transformations that are simply endomorphic. As we said, we can efficiently essentially do membership to the set of fixed point transformations, right? Okay, because we can essentially just minimize this convex function. If it takes on value 0, then we've demonstrated that our phi is having a fixed point, and if it takes on non-zero value, then we have the problem. So what's the problem? The problem is the set of transformations having fixed point is non-convex, okay? So we can't just instead minimize over the set of fixed point transformations, right? You cannot run FTRL over a non-convex set. Cool. Okay, or you don't get the regret guarantee that you would have otherwise gotten if you were running FTRL over a convex set. Okay, so we've got this egg. The yolk is convex, right? The set of endomorphisms is convex, right? An endomorphism mixed with an endomorphism is an endomorphism. And then we've got this egg white where we can do membership, all the good stuff. It's all we need, except it's not convex. Okay, so what do? What we can do is if we have a point outside of the egg white, we cannot separate it from the egg white itself because it's not a convex thing. But what we actually show, is kind of the first key idea, is that we can efficiently separate a point outside the egg white from the yolk, okay? So, if again, right, let's take this phi, this transformation, try to minimize this convex function over phi. It takes on strictly positive value everywhere. It doesn't have a fixed point. What you can do is you can, compute the p star that minimizes this function, and, you can prove this inequality, which effectively shows that for whatever p star is and wherever it gets mapped, every transformation is going to map, every p is going to be mapped in that direction in some non-negative capacity. So then what you can consider is the point p out, which is furthest in that direction in p, and provably what you've shown is that this p out must exit the set, right? Whatever the image of this p out is, it must be on the other side of this hyperplane, okay? So what does that mean? It means that we've come up with a way to separate phi from this yolk relative to this inequality, right? So, essentially everything in the yolk satisfies the following, that when you consider the image of p out, it's going to be on the correct side of this hyperplane, right? Because it's going to be an endomorphism. Whereas this phi, guaranteed, put this p out on the wrong side of the hyperplane, okay? So this is a linear constraint in phi, and thus is a linear separation between this guy and the yolk. All right, what do we do with this? So we call this semi-separation, okay? Is there a question?
Yeah, just clarifying.
Yeah.
Can you just say again what the egg white represents?
The egg white is the set of matrices that have a fixed point in P, right? So an endomorphism will have a fixed point in P, based on Brouwer's, for example. But you can imagine a matrix that expands but still has a fixed point. Some things are exiting the set, but this is not a convex set. Okay, cool. Well, I'm going backwards. A lot of builds on this stage. All right, here we go. Should render this as a PDF. Okay. We got semi-separation. We can either say, yes, I'm in the egg white, or no, I'm not, and I can separate you only from the yolk, not the white. What do we do with this? This is kind of the whole idea of this paper. It's we're building all of these things off of semi-separation as opposed to separation. So what can we do with this? We start with, this upper bound on our set of endomorphisms phi. We do this by making a standard assumption that our set P at least contains some ball of small constant radius r, and is contained within a ball of radius capital R. That gives us at least a naive upper bound on the set of endomorphisms. We can consider the set of transformations that take the green and make sure it stays within the, red. And then we just have to have some baseline upper bound, something containing the yolk, okay? Then what we do is the following. We essentially just try to run the Gordon-Greenwald-Marx algorithm on this set phi tilde, okay? Let's say it spits out this transformation phi, and it happens to be in the egg white. Then we're gonna be happy. We'll say, okay, we'll play the fixed point of this phi and just move on with our lives. If instead, at some point, the algorithm suggests a transformation phi that is not in the egg white, well, that means that we have some capacity to separate that point from the yolk. And what that means is we can then update our prior on this phi tilde. And now consider phi tilde that is, cut by this linear plane. Okay, and now we then repeat. And now at each time step, oh, I went backwards. Oh no. Okay, but at each time step, we are now just going to continue to just query this algorithm. It's either going to cut phi tilde and give us an even better, we either improve our understanding of where the yoke is, or we just play an action that is valid, because all we actually really needed for the proof was to play something that has a fixed point. So either way, we're happy. We get linear swap regret for arbitrary action sets in polynomial in the dimension, square root of t. Per iteration, this is efficient, right? We're not querying a whole capped sphere, nothing too crazy. This has applications to computing correlated equilibrium efficiently, as was discussed. You could have players in a game minimizing swap regret, attaining this correlated equilibrium. You could also, again, like the ellipsoid algorithm is also something that uses a separation as the subroutine, right? Like we just repeatedly call separation and chop up this ellipsoid. You can similarly use semi-separation here and do a similar semi-separation ellipsoid and compute linear correlated equilibrium quite efficiently. And that's what I got for you today. Thank you.